So if Gianni doesn't wave, please feel free to wave if you think I'm going too quickly. So firstly, I should also mention two of my colleagues who work with me in the laser ablation at BGS. That's Elliot Hamilton and Andrew Marriott. And in fact, you can see here, Andrew on the left, you can only see the back of his head. That's actually the prettier part. He's better from behind. And on the right is Elliot. He's very tall, and we make jokes about this. Anyway, you can see here right in the center the important bit, which is our new laser, and then behind this, our ICP-MS. I will also try and remember to give the names of various archaeologists that I've worked with along the way, and I hope if I forget them, they will forgive me. So today's talk, I will start by what is laser ablation, and then a little bit about the instrumentation and the method. So if you are an analytical chemist, please stay awake at the beginning. But if you are an archaeologist, you may fall asleep for the first 10 minutes. If you are archaeochemist, then you must listen to everything. Then I will talk about some archaeochemical examples. Firstly, flint. Then some about glass, which is probably a little bit bigger. The section is what I've done most work on recently. A bit about pottery, ceramics. And finally, some of the more unusual materials that we might be able to use laser ablation to analyze. And finally, please feel free to ask any questions. No question is too simple. So firstly, people ask me, Simon, what is laser ablation? How is it that light can remove material from the solid surface of my sample? And so this is the analogy, the simpler explanation I give. So for 1/10,000,000th of a second, so an incredibly short period of time, we focus the power equivalent to a nuclear power generating plant. But we focus that as a spot of light into the diameter of a human hair. And this is enough to vaporize maybe 1 microgram of sample. And for the archaeologists, this is the important bit, because particularly archaeologists from museums will say, are you going to damage my sample? If you do the laser ablation right, they will need a microscope to see the sample you have taken, the 1 microgram. And the laser then makes what's called a microplasma, and in fact you can see this is here. This is actually a picture I took for my PhD 30 odd years ago. And so this is a plasma, very hot, and you can see particles coming off. So this is actually some steel ablated in air. Normally for the analysis we do it in a different gas, but the steel particles burn in the air so you can see them coming off. And here on the right we have captured with a filter some of the particles. This is a big particle. Actually, most of the material is very fine, below 1 micron, and you can see this perhaps in the background. So, for what laser systems are available and why would we use them? There are 3, maybe 4 major laser types available to use. So if you were to look, do a Google search on laser ablation, any of these might come up. The first, the neodymium-ionic at 266 nanometers, is a relatively small laser, but it's mostly used for biological systems now, and it's the cheapest one. The next up is the neodymium-ionic at 213 nanometers. So this is more into the ultraviolet. The shorter the wavelength, the better the material you are analyzing will absorb the laser, and typically the better the ablation. These are still relatively small. They are good for most materials, and they have a middle cost. And this is the one you have in Valencia. It's actually a very common choice in many labs, particularly because of the size. The next is the Excimer, the argon fluoride gas at 193. This is significantly larger. It's particularly good for transparent materials like quartz. And so for the geologists where I work, they like this. but it needs special gases and it has a high cost. And finally, now there are some things called femtosecond incredibly fast lasers. They're very rare, they cost incredible amounts of money, and there are maybe only 10 used for laser ablation in Europe, if that. So having the 213 here in Valencia is perfect. So we use the laser to make the microsample of our material. So we want to analyze that, so we need to get that into the mass spectrometer. So how do we do this? Your sample is sitting in a cell, in a sealed box, and you fire the laser through a window, and you observe your sample and choose the area through the window with a microscope. And you make the ablation, you produce the particles, but we have helium gas flowing through this cell, this box, and this blows the material into the ICP-MS. We actually mix some other gases at the same time, but this is just to help the mass spectrometer. But the main thing is that we sweep the material from the sample into the mass spectrometer. And actually we can see here for Rio, on the left, this is the head of the laser, and down here, this is the sample tray, so your sample would go in here and goes in the drawer. You fire the laser through one of these lenses, and over here in the center we have some tubing that takes it into the mass spectrometer on the right. In fact, if we are doing very, very small samples, or we are mapping samples, you actually can have a special torch for the ICP-MS. But if anybody is really interested in that side of things, talk to me afterwards. Okay, a little bit more about the cell where we do the ablation. So in the box you have typically several samples sitting, and that there is a cup within the chamber that is on an arm, and down here, this is the cup sitting over your sample. The laser fires, hits the sample, makes the particles that go into the small cup, and then the helium gas blows it off to the ICP-MS. Normally we use helium gas for this because it's better at the particles, the very small particles, are maintained in the gas stream better in helium than they are in other gases. But previously people would use argon, and unfortunately now the price of helium has got incredibly expensive, and I actually see the day, maybe in a year or so's time, particularly with the problems in Ukraine, where we all might not be able to have helium gas, and we might be going back to using argon again. If we just make a single pulse of the laser, normally we would do more for the analysis. This is the signal that you get. You get a very sharp peak, and then it decays away. And 90% of the sample will be transported to the mass spectrometer in just 300 milliseconds. So what this means is, if you are doing different elements, you must jump between the different elements, the different isotopes, very quickly. And that is why the ICP, the quadrupole ICP mass spec, is very good. But it also means that there is really, can be a finite number of isotopes you can do at one time. Unless, oh, okay, we'll come back to the unless in a minute. I changed the order of the slides. With all instrumentation, you are always making compromises. That many times people want to analyze as many isotopes elements as possible, so maybe 40 or more. But each of those has slightly different properties in the mass spectrometer. and optimizing for them can be quite difficult. So we did some experiments where we were changing the plasma power and the helium gas and the argon gas, and in order to understand what was going on, we must use some multivariate statistics. So we did some factor analysis. And what we see is that many elements behave as one group. So these are the rare earth elements that Gianni likes very much, some of the major elements like calcium, magnesium. But other elements like sodium and silica and potassium behave in exactly the opposite way. So what it means is, if we see that down here, we actually end up with some compromised conditions. You have to be very careful when you are making your selection that what is the most important elements to you. And often they may be the ones with the lowest concentration, because if the element, another element that might be important, if there is a high concentration, it doesn't matter if you do not analyze it with the optimum conditions. I said before that we have some very 300 milliseconds is the time for the material to come out of the chamber. So if we were to fire the laser at 1 hertz, 1 pulse every second, we would get these spikes, which is not very good for the analysis. So one of the things you can do is you can look and you can change the frequency of the laser, how fast you are running, how many pulses per second. And what we find is that here, if we fire the laser at 20 pulses a second, we actually end up with a very, the smoothest peak. And this is the best for making spot analysis. But if we want to make maps, and I will explain about some maps a bit later, actually we need to go much faster, more like 100 hertz. So we have a very sharp signal. But here, so today with Gianni, we were using 20 hertz. So, and your laser, it's the same speed as on ours. Okay, so that is really the end of the chemistry. So the chemists may go to sleep and the archaeologists must wake up. So, my first example is about flints, provenance of flints. And this started with a project in 2008 with Professor Paul Pettit, who is now at Durham University, and Marcy Rockman, who was at the time working for the USGS. And they were interested in hunter-gatherer behavior in the landscape and reconstructing patterns of the British late Upper Paleolithic, so 14,000 years ago. And the idea was to use the laser ablation of flint tools to look at transport and trading and mechanisms. But to do this, we needed a database of real samples. So Paul and Marcy went out and they collected type material from the Yorkshire Wolds, the Lincolnshire Wolds, East Anglia, North Downs, Chilterns, which is up here, Wessex, which is here, and Beer down here. So we had this type material from modern exposures, and this unfortunately is one disadvantage of collecting material now for the Paleolithic. 14,000 years ago, the exposures of the material may have been very different to now. You know, we can go and we can find a cut where a new road has gone through, and we have the exposure, and we can find the nice flint. But probably 14,000 years ago, this might not be the place that the Paleolithic man was collecting the samples. So we just have to be a bit aware that when we take the modern samples, are they representative of what the original people who made the artifacts were able to sample? little bit of chemistry. So one of the things that was important we wanted to know was if you sampled different places on the flint, did you get the same number? So what we did is we would do a group of 3 ablations very close together, and then move maybe 5 millimeters or 10 millimeters away and do another group of 3, and then do another group of 3, another 10 millimeters away. So here, for this FS13, this is the first space, then 5 millimeters, then another 5 millimeters away, and then there are 3 analyses at each point. So here we can see for uranium, actually for this sample, the 13, the Pew, very consistent. For the FS2, not quite so consistent. For lithium, on this occasion, it was consistent for the FS2, but less so for the others. So we do have to be aware that with the laser, we are making a very small sample, and is that sample representative? So you must always think about a sampling strategy that will be as representative as possible. We, of course, generate huge amounts of data. You fire the laser for less than a minute. So in a day, you will generate hundreds of spots sometimes, and for 40 elements. So with this large amount of data, we have to use multivariate statistics. We have to have ways of handling big data. The other thing is that something people often forget about is, and this has been known for geochemists for a long time, that trace elements are log-normally distributed. So before you do a lot of the classical statistics, you have to transform the data. So here we have some principal components analysis. We did 33 elements, and then we can reduce the dimensions down to about 6 or 8. And by using various things, we can group the elements. So factor 1 was typically associated with rubidium and aluminium, potassium, whereas factor 2 was associated with zirconium and niobium and barium. And in this way, we were able to separate, with 2 factors, we were able to separate maybe 4 of the groups, and the others would cluster together. And then if we looked at the higher dimensions, so if they here 3 and 4, we would separate different groups. So on this graph up here, I've just circled the areas for the different type of material that we collected in the field now, and then overlaid the spots are from real artifacts. We have material from 3 sites, from Bradgate Park, Farndon Fields, Creswell. All 3 of these sites are in the Midlands, and I will show you on a map in a minute, and Way Manor, which is in the south of England. And we can see here, really the easiest thing to see is that actually the Creswell ones do not match with any of the samples that we took. And, well, maybe this one does, but these don't. So although we sampled 8 or 9 regions, and within each of those regions there were 3 sites, it's still not enough. Maybe there were some exposures that the ancient man had that we don't have now. We were more successful here at the Farndon Fields. They are on the edge of the North Lincolnshire and East Anglia. And when I show you on a map in a minute, you'll see that that's not unreasonable. Whereas Way Manor, these squares, which is in the south of England, match Salisbury, which is also in the south of England. Okay, so here is the map. So first of all, the area we're talking about is in the centre of England here. Bradgate Park is maybe 10-15 kilometres south of BGS, where we are in Nottingham. Farndon Fields is maybe 20 kilometres to the north and to the east, and Creswell Crags maybe 40 kilometres north. So what is important for the next part of the talk is that now, this year, just literally a week ago before I came here, we started to do some new work on the material from Farndon Fields. This time with a local archaeologist called Daryl and Sue. And these are, well, Daryl is a professional archaeologist, Sue is an amateur archaeologist. But what was different this time is the site at Farndon Fields has been, because it was actually looked at now by amateur archaeologists, over several years they have spent many days out collecting material. So each of these spots on the map is a find on the surface. And this is maybe 2 kilometres by 1.5 kilometres. So several times they have walked the fields here. And this is actually a road going through the centre. Because actually the site was first found when they built this new road. By chance they found that there were some flints. And subsequently they have done some test pits that are maybe a metre square. And so this is the test pit. They have mapped the finds within the test pits, and right down to they have been sitting to a very small size. So they have collected many tiny flakes. And so one of the questions was that these mini flakes, the députage, we've taken from a single pit, and we have about 40 samples from a single pit of these small flakes. And what we wanted to know is, can we decide from the chemistry, are all these flakes from 1 or 2 original bigger samples probably all made at the same time? Or were they made just one at a time, maybe one year and 2 the next and 3 the year after? So this data is literally from 2 weeks ago. And it looks like we have probably 1 sample here, maybe 1 or 2 here. But the other thing I want to bring up is the issue of alteration. So in flints, the British call it cortication. So if the flint is white, it's been the silica has been hydrated, it's been interacted with the ground, as opposed to the dark, fresh flint. And of course, most of the flint that we collected for our study around the UK were fresh flints. But with the cortication, with the alteration, has it changed the elemental signature? And actually for these elements, it looks, the corticated, the altered material overlaps pretty much the unaltered material. So for these 2 elements, they are okay. But now I have to go and look at all the other 40 elements to decide whether they are reliable with the natural alteration that we see in the samples. And of course, the small flakes have a big surface area, and so they are more likely to be altered. Is the speed okay, Gianni? Okay, so that is enough for flint for now. Now I would like to say something about glass. In fact, the reason that I am an honorary research fellow at Nottingham is because I have done a lot of work with Professor Julian Henderson, who is an expert on glass, ancient glass. In fact, he was originally a physicist, but many years ago turned into an archaeologist. But glass is iconic. It's one of the most beautiful of the ancient artifacts that we have. And glass has been around for much longer than most people think. One of the studies I'm going to talk about in a minute is Hittite glass. I can never pronounce this, Bukalali. I can't pronounce in central Anatolia. And here they have what people have questioned is actually the earliest piece of a glass vessel. And we got to analyse this. A lot of what we have been doing is provenance and technology. So actually in making glass, ancient glass, there are two primary technologies. Both of them use silica, and that could be in the form of either sand, you see here in the background, or it could be pebbles. But it's the flux, the alkali, that can be radically different. So first there was plant ash glass. So you burn the plants, you take the caustic ash, and react this with the quartz. And then in the late Iron Age, they started to produce glass with mineral flux, so netron from Wadi Natron in Egypt. And then later, in the 9th centuries, we went back to, particularly the Islamic people went back to plant ash glass. So the primary elements that you need for making the glass from the ashes are sodium carbonate and calcium, but it brings with it magnesium, potassium particularly, but also phosphorus, chlorine, strontium, lithium, boron, rubidium, barium also come in with the plants. And depending on the plants and where they were grown, you will be bringing in different amounts of these trace elements. This Salsoa jordanicola is probably the one they think was most commonly used. But equally, you will bring in some different elements with the quartz. If it's a pebble, then you will bring in very little other elements. But sand, often there are, if you look at some sand and go on the beach, you will see there are some dark specks, and they are other minerals. So the other minerals might be feldspars, they might be magnetite and iron oxide, they might be zircon or zirconium silicate. So other elements that come in include titanium, neodymium, zirconium, chromium, niobium, rare earths, etc. So this is how we're going to end up with our fingerprint. Small pieces of glass we can put straight into the laser to analyze, but actually before people were doing much laser ablation for glass, they were using electron probe, microanalysis, and SEM and EDX, for which you need a flat sample. So here in the center we see a piece of plastic where there are some small pieces of glass embedded, and the people get very skilled at just flaking a very tiny piece of glass off a larger piece, embedding it in the resin and polishing to a flat surface. And actually this is ideal for the laser as well. And usually most of the people I work with have already done the EPMA or the SEM on their sample first. The other advantage of this is that because you are polishing a new surface, you do not have any contamination or alteration on the surface. Because glass, when it sits in the ground, you will leach some sodium, some potassium from the surface. And because the laser only is sampling maybe 10 microns on the surface, if you do not have a fresh surface, your numbers for sodium, potassium may be wrong. Okay, so the first example was some work we did on glasses from the Middle East. These are Islamic glasses from the Muslim times, and we have samples from the Western zone. So we had samples from Cairo, Kirbat, Damascus, and Beirut. We had what we called the Eastern zone, so Samarra, Baghdad, Ctesiphon, and in the extreme east, Nishapur. But we also had some samples from Al Raqqa. Julian was lucky enough in the 1990s before all the problems in this area, to actually go and excavate a primary glass kiln. And if any of you have worked with glass, you will know that finding a primary glass kiln, not just a small one where they have been working glass, but where they have make the primary glass, are very, very rare. So we have some material from our Raqqa, and so one of the questions was, did the El Raqqa material, was it like the Western Zone, or was it like the Eastern Zone? Or was it something different that we could tell? There are some analytical challenges when you're doing the glasses, particularly for elements that are used in colorants. So, in one sample here this sample, we're up here in the green, we have 3% copper, more than 30,000 parts per million. And then another sample, which is not coloured with copper, we only have 13. Tin, which is used as an opacifier to make the glass less transparent. You can have 60,000 parts per million in one sample, and then 5 parts per million in the next. So actually, when we do the analysis, we have to be very careful if we have very high levels and then very low levels, that we spend some time between the samples so we don't cross-contaminate. One of the things that we have managed to do with some statistics is we can actually, most people using cluster analysis to cluster the samples together, but you can actually equally cluster the elements together to see the ones that behave in certain ways and that behave as groups, and then you can start thinking about which raw materials are they associated with. Are they associated with colorants? So this is a way of learning about the technology. So here we can see these elements grouping together: lithium, magnesium, potassium, phosphorus. These are all classic elements that you would get from plants. Sodium and silica. This is probably from the quartz. Calcium and strontium. Most glass that is going to survive well has to have some calcium in it. Now, that calcium can come from the plants, and maybe it's enough, but if you want to get the best quality glass, actually you have to add some more calcium. Or if you make the glass with the natron, with the mineral flux, you have to add some calcium. Now, sometimes, if you use beach sand, that calcium will come from shells. But other times, if you're making it inland, and I was talking about the eastern and the western zone, in the eastern zone, the sand is not going to have shells, whereas near the Mediterranean coast it will. So they would have to perhaps add limestone. And then we have a group here, which are the colorants, a group here, which are minerals you will find as heavy minerals in sand and so on. So, okay, here we have actually quite a simple graph, which is just the iron concentration versus the chromium concentration. These are both elements that I would expect to find as impurities in the sand. So chromium from a mineral called chromite, and iron from magnetite or hematite or something like this. And actually, we get, so I should explain first. So the western zone are in grey, and we see them down here. The eastern zone are mostly in colour, except for the Raqqa, which are in blue. And so the lower chromium ones are from the western zone, the higher chromium ones are from the eastern zone, and conveniently, many of the Raqqa samples sit in the middle between them. That is just getting the data or the information from two elements. So if we use ratios, we can increase the number of elements in the graph. So here I have chosen lithium divided by potassium and cesium divided by potassium. And again, we can see some separation. Actually here we start to separate the individual sites in the west, and to a certain extent some of the sites in the east. And again, the Raka ones are sitting in the middle. Those alkali elements are almost certainly from the plant ash. So coming back again to elements that are associated with minerals in the sand, we have chromium divided by lanthanum this time, and zirconium divided by titanium. Actually, I should not take credit for this graph. Andrew Shortland published some data for Mesopotamian glass and Egyptian glass back in 2007, and actually many people, us included, have found this a very useful graph, even if we are not looking at Egypt or Mesopotamia. But again, here using this graph, actually it separates the samples from Ctesiphon, many of the samples from Ctesiphon well, and the samples from Samara here, and Nishapur here. Okay, back to, I was talking about the Anatolian samples. So particularly the Japanese have been working with the Turkish archaeologists on some late Bronze Age and early Iron Age sites in central Anatolia, where they are finding glass. And at first, everybody expected that the glass in Turkey probably was either originally from Greece or Egypt or Mesopotamia, all areas that were known to have used glass in similar time periods. And of course the Turkish people wanted to say, would like to say that actually the glass was made in Turkey, it wasn't imported from somewhere else. So Julian and I worked with the Japanese people and some Turkish people on this material. We had particularly beads and segmented beads. So up here, LBA stands for Late Bronze Age, EIA is Early Iron Age. Well, what was very interesting was actually the Late Bronze Age glass had a much tighter distribution. The Early Iron Age glass, it looks, the signatures, the chemical signatures were much wider. Yeah, much more compositional variation in the early Iron Age glasses. Two different elements, aluminium and thorium, and again we see a relatively tight group for the Late Bronze Age. Actually, the early Iron Age turquoise beads are similar to the turquoise beads from the Late Bronze Age. So one of the things that we can say is for this particular colour and type of bead is that there is a continuity of the technology and the sources of material between the Late Bronze Age and the early Iron Age. But for some of the other colours in the early Iron Age, they have a very different chemistry. And in fact, the Julian, I'm not so convinced, but Julian's quite convinced that they were probably from Mesopotamia. Okay, I mentioned just in passing about mapping at the beginning. Actually, one of the reasons for us buying a new laser was to be able to make chemical maps. Rather than just making a spot of analysis here and a spot of analysis there, we actually want to map samples. Glass was not the most obvious thing to want to map. Usually people would imagine that glass is going to be homogeneous. But of course, actually, if you look at many pieces of glass, it's most attractive when you have two colours in the same, or more colours in the same piece of glass. They may be wrapped and twisted in beads. It might be applied trails of thin pieces. So actually looking at more than one colour at once could be quite interesting. And particularly, something will tell you about the temperature at which the piece was made is that if you have a higher temperature heated for a longer period, you might expect some diffusion, instead of there being a sharp chemical boundary between the two different colours of glass, you might expect that there would be a gradation between them if the temperature of the production is higher and it's heated for longer. So here I have what was nominally a two-colour piece of glass. So the first element, aluminium. So the different colours are the different concentrations. So here we have a scale bar. And this is quantitative. But the colours are random. So actually the amount of aluminium in both colours of glass was almost exactly the same. Here we have in the middle tin. It's much higher in the top of the glass. In the lower part of the glass, here we have blues and oranges. But actually, interestingly as well, it's not very well mixed at the lower concentrations. You can see bands. And actually, visibly on the glass, you cannot see these bands. But with the chemistry, we can see. So this glass was not as well mixed as the top glass. And then with the copper, high again on the top, but here it looks as though we have a zone of mixing, some diffusion between the high on this side and the low on this side. And then again, the copper is also not perfectly mixed because we have a little bit higher at the bottom here than in the middle. So with the mapping, we can make some understanding of the technology. Okay, my third material is pottery, for provenance. So the first thing I think with ceramics we must consider is that they are naturally not homogeneous, certainly compared to glass. There is often the deliberate introduction of temper, and that is sand or pre-fired pot or some shell. Many different things are used, along with the basic clay, the kaolinite or montmorillonite or whatever the mineral clay is. So, laser ablation with a small spot size may not be appropriate. And in fact, there is a very recent paper by Van den Norberg on some samples from Belgium and Neolithic pottery, and he says, don't bother with laser ablation for pottery. And in fact, previously, normally I have not done laser ablation on pottery. I did a lot of work in the late 1990s and early 2000s with some Scottish people on pottery, chemotyping pottery, and I think I have a diagram in a minute. But now I would say we have there is an alternative view we can consider. If we are using the laser, we can avoid the coarse grains, the temper, and maybe we can fingerprint the pure clay. But you must be able to see in a section of the sample where is the pure clay and where is the temper. Or you can make the chemical map. Okay, I'll come back to that again in a minute. So this is just some solution data from the 1990s, early 2000s, where we were separating different groups of Scottish pottery, particularly redware pottery, from the medieval period. The thing about the medieval redware pottery in Scotland is actually most of it looks very similar. It's just red pottery, and unless you know a lot about the site, it could be from 1200, it could be from 1500, it could be from 1800. It looks exactly the same. And this is why they were particularly interested in using chemical typing for the pottery, because visually they couldn't tell the difference. So, mapping. So actually this is some work with a guy called Alex Su. He's actually originally Hong Kong Chinese. These are some ceramics from Southeast Asia that he's been working on as part of a contract with the Chinese University of Hong Kong. And they wanted laser work because actually they were interested in what was the relationship between the glaze and the body of the pottery. So actually in this map here we can see at the top here, we can see quite nicely the magnesium in the glaze here. This is the magnesium in the body, much lower. But actually interestingly there is an underglaze that they didn't realise was there, where there is almost no magnesium. With sodium, however, we see not so much, and poorly, not evenly distributed in the glaze, but higher, and more variable here in the body. And at the bottom here, manganese is particularly associated with some inclusions, the high levels of manganese. But what we can do is try and use the laser to separate the chemistry of the inclusions, of the body, of the glaze, the underglaze. And we can start to do phase mapping. So here, the colours here are mixing colours of potassium, iron, and calcium. So two different types of clay will have different calcium and potassium ratios, amounts, and the iron is the iron oxide that is often in the clay. So what we can see here, we can now start to see this phase here, this inclusion, is iron and calcium rich, and there are several examples of this inclusion. Whereas down here, this one is blue, more blue, this is just more iron rich. But also we can integrate the signal along a path here. So this diagram, as I've extracted the barium, information for barium, so we can see here, if we follow this red line, this is the glaze, has the high barium. Then we come to about 600 part per million barium in the clay body here. Sorry, here. And then we hit an inclusion here, and we see the barium drops. And then we are back into the more normal matrix, and we can see we get about 600. But in fact, it is occasionally a little bit higher, maybe some other inclusions. So here we are using the mapping to make the phase information, to separate the glaze, the underglaze, the body, the inclusions. So actually, one of the things that I want to go back to when we did the work on the Scottish pottery, there were some unusual inclusions in pottery from one particular region, and we are very convinced that they are associated with the local granite. So now I'm hoping that I can do with this phase mapping and the work with the laser ablation mapping, that I can go back and look at the samples that I had 20 years ago and actually be able to say, yes, this inclusion is from the granite that is 5 kilometers away. Okay. Unusual archaeological materials. Utilis, fish ear bones. I've done a lot of work on fish ear bones. I will say now I have never used them in archaeology before now. But maybe soon an archaeologist will come along and ask about it. But otoliths are the calcium carbonate hard part of a fish that often survive in the middens of fish-eating ancient communities. And I was in the States, visiting the States, and saw an old mound, midden mound that was maybe 20 meters high, which they had made a section through, and they had some fish otoliths from this midden. But their shape and size are quite distinctive by species. So that's the first thing. So you don't need a laser to do this, you just use a microscope. The ear bone grows daily and has regular bands like tree rings. The chemistry of the ear bone changes with the water chemistry and with changes in the fish biology. So, for example, salmon move between freshwater and seawater. They are an extreme example. So, part of their life they're living in freshwater, part of the life in seawater, and the concentration of the elements is not surprisingly radically different. But even within freshwater or seawater, you will have some changes in chemistry. But also, if the fish's different parts of its life cycle change, so when it becomes mature and it starts to breed, actually some things change in its chemistry, its body chemistry, and that is reflected in the ear bone as well. There was actually a very nice paper by Dispain in 2013 on the couples, the morphology, the size and shape of the ear bones with the chemistry for otoliths in mid-material in Australia. I'm going to show you an example from modern ones because, as I say, I've not worked on archaeology. A colleague of mine, actually a former student, Phil Hollyman, is a marine biologist, and he now works for the British Antarctic Survey, and they go and collect the ear bones from these very large toothfish that are found in South Georgia, which is in the South Atlantic, nearly to the Antarctic. And what's interesting, this is not pretty. There's supposed to be some text here, but for some reason it's not quite right. But anyway, he's been collecting the otoliths and he's been looking at these, and we have been making maps of them. And actually, this is this should have been a why we use this software I like for working with laser ablation. But Gianni will now say that why we work with this is we've spent 2 days with problems with this, but actually when it works very well. So we make these maps of the fish's ear bones, and so here this took about 45 minutes to map. It's about 5 millimeters long, maybe more than that, 8 millimeters long and 3 millimeters high, and we can see the strontium chemistry changing as it's moved. The fish is moving between different bodies of water and actually between different parts of its life cycle. So in the very center here, this green in the very center is actually the signal from the mother with the egg sac of the fish when it's born, and then it's a juvenile fish and it stays in the nursery area, and then it starts to move into deeper water. But actually we can make these maps selectively quite quicker. So this here, down here, is a strip from the middle, across the middle here. So in 10 minutes we can make a map, and actually we can make even narrower maps and with even more resolution here. You're probably seeing almost here in the middle, just a slight change in the colour. That's probably 2 or 3 days where it has moved between different bodies of water. Okay, and then yes, just some more pretty pictures. Okay, that's almost exactly 1 hour, a little bit. I said 45 minutes, and then I thought, well, I must speak a little slower, so maybe close to an hour. It's an hour. Thank you for your attention. Please, any questions? If you are too embarrassed, then you can find me afterwards. Okay, well, Gianni has my email. You can find me afterwards.
No, but now are going to talk. Don't worry. They are just astonished from your
Gianni, maybe you should stop filming.
presentation.
Stop filming.
But it's the funny part. Okay.